Hey guys, what's up? Let's meet today again to revise the chapter in one shot, Haloalkanes and Haloarenes. And I'm here to give you some very important tips and tricks to revise this chapter so as to score very good marks in your board examination. So this entire content, which is actually of 10 to 15 minutes, will give you a complete insight to solve the complete the sequence type questions, the conversions which the children feel very difficult, what happens when type of questions, for example, what happens when chloroalkane is treated with AGF. So we will discuss such type of questions. Then name reactions we will discuss, and word problems. All these type of questions you will be able to easily do if you study this content thoroughly. So I have briefed and summarized the content in a very short form, and let us proceed with that. So the very first conversion tip here is that when chloroalkanes are treated with aqueous NaOH or moist AgOH or water, we can convert them into corresponding alcohols. Very, very important, and it's a nucleophilic substitution type of reaction. Remember, Cl can be converted to OH by the use of reagents. Number 1, aqueous KOH or NaOH. Number 2, moist AgOH. Number 3, water. Any of these can be used. So number 1 tip. Number 2 tip, reverse if we have to do. For example, we have to convert alcohols to chloroalkane. In place of OH, we want Cl. Then we can use either of these reagents for the conversion purpose. Either we can use phosphorus trichloride, PCl3, phosphorus pentachloride, PCl5, thionyl chloride, SOCl2, and this reaction is called Darzon's reaction. It is the best method to convert the alcohols to chloroalkane. The reason being the byproduct SO2 and HCl being gaseous escape into the atmosphere. So, or Lucas reagent. I hope all of you remember what is Lucas reagent. It is the mixture of anhydrous ZnCl2 and concentrated HCl. So, OH to Cl can be converted with either of these reagents, PCl3, PCl5, SOCl2 or Lucas reagent. Now let us talk of the third reaction, the third reagent, and that is ammonia. If you treat alkyl halide with ammonia, the reaction is a very, very important reaction which is called Hofmann's ammonolysis reaction. You can convert them into amines, 1 degree. Further, 1 degree can be converted to 2 degree on treatment with excess of alkyl halide. Further, 2 can be converted to 3, and finally you may get quaternary ammonium salts. So this is Hofmann's ammonolysis reaction, treatment of chloroalkanes or haloalkanes with ammonia to form amines. Next is a very important reaction. So we will study these two reactions in a combined manner and in a comparative manner. So just you have to recall that when haloalkanes, they are treated with KCN or maybe NaCN, then cyanides are formed. But when treated with AgCN, which is a covalent compound, isocyanides are the major products. Remember, in the same manner, the somewhat similar reaction to this is that when haloalkanes are treated with AgNO2, then you get RNO2, that is nitroalkanes. But when treated with KNO2, which is an ionic compound, then you get nitritoalkanes. Remember, if you just remember and recall that what do we call these groups as? We call them as ambident nucleophiles. Ambident nucleophiles are the ones which have 2 donor atoms, but the attachment to the parent hydrocarbon chain takes place only through 1 atom at a time. Next is again a very important reaction, alcoholic KOH. The role of this is to carry out dehydrohalogenation, removal of hydrogen halide, removal of HX. So here, when any haloalkane is treated with alcoholic KOH, alkenes are the major product. As a result of elimination reaction, more specifically, dehydrohalogenation will take place. Then we have 3 reactions, we will study them in a comparative manner so that it is easier for us to remember and recall. So, reaction with sodium metal. So, we can treat alkyl halides with sodium, we can treat aryl halides with sodium, we can treat a mixture of alkyl and aryl halide with sodium metal. So let us treat alkyl halide with sodium. We get alkane containing greater number of carbon atom. So this is an ascent up reaction. In the same manner, when two molecules of aryl halides, that is chlorobenzene, are taken, treated with sodium and dry ether, we get biphenyl or diphenyl, and this reaction is termed as Fittig reaction. But when combination of these two, that is one molecule of aryl halide and another molecule of alkyl halide is taken and treated with sodium, we get alkyl derivatives of arenes. For example, here we have got toluene, since we have taken chlorobenzene and treated it with chloromethane. So this also with sodium, and all these three reactions are with sodium, named as Woods reaction. Fittig, when two molecules of aryl halide are taken. When one of alkyl, one of aryl halide is taken, it is called Woods-Fittig reaction. Let us move on to 10th and 11th. We will study we will study them together. Why? Because both of them are halide exchange reactions, where we are exchanging the halogen. Let's say chloro or bromo is being exchanged with fluoro, or chloro or bromo is being exchanged with iodine. So let us study them together. When you treat chloro or bromo alkane with AgF or Hg2F2, you get fluoroalkanes, and this reaction is again an important name reaction called Schwarz reaction. But when you treat them with NaI in presence of dry acetone, then chloro or bromo is replaced by iodoalkane. And this reaction is called Finkelstein reaction. So remember both these halide exchange reactions, one giving you fluoroalkane, another iodoalkane. So fluoroalkane one, that is called Schwarz reaction, and the one which gives iodoalkane from chloro and bromoalkane, they are called Finkelstein reaction. Then cyanides, just see here that when any haloalkane is treated with KCN, we get cyanides. Now cyanides will be a very, very important class of compounds in the conversion type of questions. Why? Because they can be converted into a variety of functional groups by different treatments. So let us summarize that how or by what reagents can we convert cyanides into different functional groups. So let us see complete hydrolysis in acidic medium. We can convert them into carboxylic acid. Partial hydrolysis in basic medium. We can convert them into acetamides. Partial reduction using SnCl2 and HCl, we can convert them into aldehydes, and it is a very important name reaction called Stephen's reaction. And complete reduction using LAH, lithium aluminium hydride, or maybe sodium and ethanol. We can convert them into 1 degree amines. And this is again an important reaction called Mendius reaction. So cyanides are a very important class of compound. Then let's have a look at another very, very important reaction which will often be involved in the conversion, and that is aniline to BDC. Aniline to BDC, if you want to convert, we can do it by treatment with NaNO2 sodium nitrite and HCl at a 0 to 5 degrees Celsius temperature, and it will result in the formation of BDC, and the name of the reaction is called diazotization. Now this BDC formed is also again a very important class of compounds and can be converted into haloarenes. So let us see by what all reagents we can convert BDC to haloarenes. If you treat it with CuCl in presence of HCl, you get chlorobenzene, or else CuBr in presence of HBr, you get bromobenzene, and this reaction is again an important reaction called Sand-Meyer reaction. But if you treat it with copper powder in presence of HCl or HBr, then you get chloro or bromobenzene, and this reaction is called Gattermann reaction. When you warm it with Ki, iodobenzene is the major product. But when you treat it with fluoroboric acid followed by heat, HBF4 followed by heat, then we get fluorobenzene. In addition to that, we get the byproducts BF3, N2, HCl, and this is again an important reaction called Bals-Schiemann reaction. So once you are through with these reagents, children, it will help you a lot in solving the conversion type questions. So just prepare all these reagents thoroughly. The next conversion tip is the conversion of alcohols to chloroalkanes, which we had just discussed earlier also. Point number 2, just see. So this is Darzin's reaction. Darzin's reaction converts the alcohols to chloroalkane by treatment of alcohol with thionyl chloride, SOCl2, and is actually the best method to convert the alcohols to chloroalkane. The reason is that SO2 and HCl byproducts, they are gaseous and escape into the atmosphere easily, leaving behind pure chloroalkanes. So this is Darzin's reaction. Next is a commercial method to convert the chlorobenzene to phenol. It's a commercial or industrial method to prepare phenol. So chlorobenzene, when treated with aqueous NaOH at temperatures 623 Kelvin and 380 M, the name of the process is Dow's process. We can convert chlorobenzene to phenol. So chlorobenzene to phenol by Dow's process, reaction with aqueous NaOH, 623 Kelvin and 380 M pressure. Next is another important name reaction, formation of bromoalkanes from silver salts of carboxylic acid by treating them with bromine. So when silver salts of carboxylic acid are treated with bromine, then you get bromoalkanes along with the precipitate of AgBr and CO2 gas being evolved as the byproduct. Remember, this reaction is called Borodin-Hunt-Sticker reaction, and it is a descent down reaction because one of the carbon you can see is escaping in form of carbon dioxide gas. So there is decrease in the number of carbon atom in the product as compared to the parent acid. Next we come to the addition reaction, and this reaction has been studied earlier also in lower class 10. It is actually the test for unsaturation. It's an addition reaction, and when you add bromine, halogenation of bromine, then this bond will break, double bond will break. When it is added to alkene, 1,1 bromine will attach and it will form colorless 1,2-dibromoethane. Ethene will convert to colorless 1,2-dibromoethane on addition of bromine, the color of which is reddish brown. So how come it is the test for unsaturation? That when reddish brown color bromine gas is passed through any unsaturated hydrocarbon, then the reddish brown color of bromine gets decolorized, confirms the presence of a multiple bond in the hydrocarbon. And the name of the test is bromine water test, is actually the test for unsaturation. Next we come to this also is the content of class 11. Already we had discussed earlier also that unsymmetrical alkenes, when are subjected to hydrohalogenation, addition of HBr, then we have two conditions, whether in the absence of peroxide or whether in the presence of peroxide. So in the absence of peroxide, remember, Markovnikov rule will be followed, which states that negative part of the attacking reagent attaches to that doubly bonded carbon to which less number of hydrogens are attached. But in the presence of peroxide, anti-Markovnikov rule will be followed, resulting in the formation of 1-bromopropane. Anti-Markovnikov rule is just reverse of the Markovnikov rule. So addition of HBr in both the conditions, remember, to unsymmetrical alkenes, one in the absence of peroxide following Markovnikov rule, another in the presence of peroxide following anti-Markovnikov rule. Next is again an important reaction, allylic bromination. And when any alkene is treated with bromine, then the allylic carbon gets replaced by bromine. For example, this is cyclohexene. When treated with bromine, the condition is in the presence of ultraviolet light. Then this is the allylic carbon. Even this is the allylic carbon. Saturated carbon adjacent to a double bond is allylic carbon. So the bromine will get substituted on that allylic carbon, and this bromination is called allylic bromination. Do you remember another reagent in addition to UV light? What can be used over here? Please write in the comment section and let me know, then I will discuss with you. So this is the alkene, and when bromination is done in the presence of UV light, then it is called allylic bromination, where allylic carbon is being substituted or allylic hydrogen is being substituted by bromine. Next is a very important reaction. It is from the content polyhalogen compound, and a question often comes relevant to this, and that why should chloroform be stored in dark colored bottles only? So the reason is Because when it is exposed to sunlight, it gets oxidized and converts into a toxic phosgene gas, COCl2. And so to prevent the formation of phosgene, it should always be stored in dark colored bottles. And a small amount of ethanol should be added to it so that in case even if phosgene is formed, it can convert into a non-toxic diethyl carbonate. So this is phosgene. It is prepared by the oxidation of chloroform or when chloroform is exposed to sunlight. So that is why it should always be stored in dark colored bottles. Now we come to, in the same sequence, let us do few arrange the order type questions related to this chapter. And arrange the order type questions often come for maybe 1 or 2 mark in your board examination. So let us see. And this is number 1, very, very important, order of reactivity of haloalkane towards the SN reaction. See, we discussed in the reaction mechanism portion video lecture, we have already discussed that the SN1 reaction, the order of stability of alkyl halides is 3 degree more reactive than 2 degree than 1 degree. This order of reactivity of alkyl halides towards SN reaction can be explained on the basis of the order of stability of the intermediate carbocation formed in the SN1 mechanism in step number 1. So the reactivity order towards SN1 reaction is 3 degree more reactive than 2 than 1, but for SN2 it is just the reverse. And what is that? 1 degree more reactive than 2 than 3. And here what has to be taken into account is the steric hindrance. In 1 degree, the steric hindrance is least and therefore the nucleophile can approach the alkyl halide very easily, making it more reactive or rather most reactive towards SN2 reactions. Now we come to order of boiling point. Now just note this order. This is the general order for all the functional groups which we'll be studying in the organic chemistry. So whenever basically question comes relating to the boiling point, comparison of the boiling point of any 2 class of compounds, just remember this general order. So I am reading this order, and this order is in accordance to the magnitude of intermolecular forces. Stronger the intermolecular forces, higher are the boiling points. So alkanes which have weak van der Waals forces have the minimum boiling points. Then comes haloalkanes which are slightly polar. Then comes ether which are again polar due to electronegativity difference between carbon and oxygen. Then aldehyde and ketones have dipole-dipole forces which are stronger than the van der Waals forces. Therefore, they have comparatively higher boiling point. Then 3 degree amines, then 2 degree, then 1 degree. 1 degree amines have maximum boiling point because there is greater extent of hydrogen bond formation due to greater available sites in 1 degree as compared to in 2 and 3 degree. Alcohols are comparatively more higher than amines. The reason is here the hydrogen bonds formed are more stronger than those formed in amines on account of high electronegativity of oxygen. And finally, carboxylic acid have the maximum boiling points among all class of compounds because they have extensive hydrogen bond formation which results in dimeric association. So remember, this general order will help you to solve the reasoning questions also and arrange the order type questions also. Next is order of boiling point. This also comes as a reasoning question for 1 mark that discuss why the para-dichlorobenzene has higher melting point in comparison to ortho-dichlorobenzene. So remember that para-dichlorobenzene is more symmetrical, and greater the symmetry, more effective is the packing in the crystal lattice, greater are the intermolecular forces, and higher will be the melting point. So symmetry and melting point are directly proportional. Greater the symmetry, effective is the packing. Effective the packing, greater is the IMF. Greater the IMF, higher are the melting points. Next is order of polarity. What is polarity now? Polarity is basically charge separation which arises as a result of difference in electronegativities of the combining atoms, or dipole moment, which is a measure of degree of polarity in a molecule. So let us compare the polarity of very, very important question which may come as a reasoning question also. Polarity of chlorobenzene versus chloroalkane. So here chlorobenzene is less polar or has less dipole moment in comparison to chloromethane. The reason is here the alpha carbon in chlorobenzene is sp2 hybridized state, and in chloroalkene it is in sp3 hybridized state. So in sp2 hybridized state, the percentage S character is higher, that is 33.3%, here only 25%. Remember, greater the percentage S character, higher is the electronegativity of the carbon. So if this alpha carbon is more electronegative, then the difference of electronegativity between the carbon and halogen will get reduced. And if the difference will get reduced, polarity will reduce, and if the polarity reduces, dipole moment will also decrease. So this is very important that haloarenes are less polar in comparison to haloalkanes. Haloarenes have a lower dipole moment in comparison to haloalkanes. Haloarenes have a shorter carbon halogen bond length in comparison to the haloalkanes. The reason is partial double bond character due to resonance. Haloarenes have a greater bond dissociation energy of the carbon halogen bond in comparison to the haloalkanes. Again, partial double bond character due to resonance in case of haloarenes. Next is order of density. And what is density? The ratio of mass to volume. Mass per unit volume is called density. So, as the number of halogens are increasing, the mass is increasing, and as the mass increases, because mass is directly proportional to density, density will also increase. And last is reactivity towards acid reaction. Again, very important. And we have already studied earlier that haloarenes are less reactive towards the nucleophilic substitution reactions in comparison to haloalkanes. Why? Because of resonance, there arises a partial double bond character due to possible repulsions, due to instability of the phenylcation and different hybridization states of the alpha carbon. So this is all about the chapter. The entire gist of the chapter is before you. Now prepare this content thoroughly from this video lecture and solve the NCERT questions. All the best.